Early natural language processing architectures like Word2Vec and GloVe share a strict design constraint. They treat every word as an atomic, indivisible unit of meaning. Each word is assigned a single, discrete identifier and placed into its own isolated silo in the vocabulary. Because of this atomic approach, a model sees no inherent structural connection between walk, walking, and walked. Despite sharing the same root, they receive unrelated numerical IDs and point to entirely separate lookup vectors. This structural blind spot causes massive data sparsity, especially in morphologically rich or agglutinative languages like Turkish or German. When a single root word can take on hundreds of prefix and suffix combinations, the model is forced to learn every single variation from scratch. The immediate consequence of this limitation is the out-of-vocabulary problem. If a deployed model encounters a word that did not explicitly appear in its training dictionary, say, breathtakingly, it hits a wall. It cannot generate a vector representation, so it throws an error and replaces the word with a generic unknown token. An atomic representation system relies on sheer memorization. If a word was not explicitly encountered and recorded during training, the model has no way to process it in a real-world application. Researchers at Facebook AI addressed this limitation by introducing FastText. FastText operates on a different approach to word modeling, one that moves beyond the idea of the word as a fixed single entity. A word is no longer treated as a single symbol. Instead, FastText models a word as a deterministic aggregation of smaller, overlapping character strings, known as subwords or n-grams. By decomposing language down to the character level, the model naturally captures internal structures. It maps the syntactic relationships between root words and their varying suffixes based on their shared sequence of letters. This compositional view provides a direct mathematical solution to the out-of-vocabulary problem. When faced with an unknown word, the network constructs a representation by breaking the text down and summing the familiar, pre-learned subcomponents. This moves natural language processing away from brittle lookups toward a flexible, structure-aware representation system. The transition from word to subword relies on an algorithmically fixed, deterministic procedure. This pre-processing pipeline executes independent of the statistical learning phase. To begin tokenization, we introduce boundary markers to the start and end of the string. This preserves positional information, allowing the model to distinguish between a prefix appearing at the beginning of a word versus the identical sequence appearing in the middle. Next, the algorithm extracts all possible character n-grams using a sliding window across the boundary-marked string. For a word like fast, a 3-character window extracts a specific set of contiguous substrings, bracket FA, FAS, AST, and ST bracket. The final step in tokenization is adding the entire boundary-marked word as a special holistic token. This dual representation ensures the model retains word-level context while still benefiting from character-level subword extraction. Because this mapping is deterministic, the exact pre-processing pipeline handles unseen test data, acting as a reliable bridge between raw text and known continuous vectors. Once the subwords are extracted, we enter the forward pass. FastText maintains 2 foundational embedding matrices for this phase, a subwords matrix, denoted as Z, and an output word matrix, denoted as U. To generate an embedding for a target word, like playing, the network queries the Z matrix to retrieve the independent vector representations for all of that word's tokenized n-grams. It then mathematically aggregates these subword vectors, usually by averaging them, to output a single, dense target vector, labeled HW. In Word2Vec, retrieving a target embedding requires a single, direct row lookup. In FastText, the target embedding must be systematically calculated, meaning here is not retrieved from a fixed dictionary entry. It is mathematically composed in real time from the specific character sequences contained within the word. With the target vector HW fully composed, we move to the interaction phase. The target is evaluated against a context word, for example, games, whose vector representation, UC, is pulled directly from the output word matrix. The model computes the dot product between these 2 vectors, measuring their semantic compatibility to generate a raw scalar score. This score is then passed through a sigmoid function, restricting the value between 0 and 1 to establish a strict probability metric. To train the neural network, we construct a dataset by sliding a context window across the source text, pairing target words with their actual neighbors to create positive training examples. We also use negative sampling. The algorithm pairs the target word with random vocabulary words that do not belong in its context. This introduces essential stochastic noise, teaching the model to distinguish between valid and invalid relationships. Using binary cross-entropy loss, the network evaluates predictions against positive and negative labels. It computes the error, triggering backpropagation to update weights in both matrices. Iteratively pushing valid subword compositions closer together and actively repelling invalid pairings is the process that shapes a robust, discriminative embedding space. This subword updating process provides a cascading downstream advantage when applied to morphologically complex, compound-heavy languages like German. When backpropagation applies a weight update to the subwords of a compound noun like Hausaufgabe, it simultaneously updates the representations of those independent recurring fragments, like Haus and Gabe, wherever else they appear across the entire vocabulary. This structural sharing proves critical when the fully trained model is deployed and encounters a novel, out-of-vocabulary word in the wild. The model tokenizes the unknown string and queries its subwords matrix for any familiar fragments. Even if the full word is completely unseen, FastText sums the pre-learned vectors of its components to infer an accurate representation without requiring a dictionary lookup. This makes the architecture effective for predictive modeling on stylistically complex historical prose, such as the works of Arthur Conan Doyle, where rich vocabulary and inflected word forms appear constantly. By distributing statistical strength across shared morphological fragments, FastText addresses the rigidity of fixed training dictionaries. In production environments, these composed embeddings are used for large-scale classification tasks, such as binary sentiment analysis. FastText rapidly parses raw text strings like IMDb movie reviews, extracting subword representations and evaluating them against learned sentiment vectors to classify the overall polarity of the document. However, inspecting these classifications reveals a vulnerability. While the model handles straightforward text well, it frequently misclassifies nuanced phrasing or inverted syntax, where the sentiment relies on the sequence of the words. This highlights a primary constraint of the FastText architecture. Regardless of how accurately a word vector is composed from its internal subwords, that resulting vector remains static once calculated. Static vectors fail to account for polysemy. The word bank receives the exact same mathematical embedding, whether the text describes a financial institution or the side of a river. FastText provides an elegant mathematical solution to morphological blindness and data sparsity. But the inability to dynamically adapt a word's representation based on the sentence surrounding it identifies the need for the next development in machine learning: contextual embeddings.